Hello, I was just reading this 4 days ago. I gave a response to Robert Holmes when he said, according to the IPCC, anthropogenic forcings since 1750 have been 2.29 watts per meter squared. The sentence construction, if you take the meaning from context, it implies one thing. If you take the meaning of anthropogenic forcings from context, it means one thing. If you take that 2.29 watts per meter squared value at all seriously, though, the anthropogenic forcings has to mean another. So let's talk about what the numbers might actually mean, and like two different ideas of forcing, because there are a couple of different definitions of forcing. Now, one of them has to do with the amount of power incoming. Here it's listed as 340.4, and subtract all of the power outgoing. And according to this chart, which was made in 2009, the net absorbed heat was 0.6 watts per square meter. But if you come down here and look at the 2019 values, it says that NASA has found that the value is more like 1 watt per square meter. And so the way I'm going to write this is the sum of all the powers coming into the system minus the sum of all powers going out of the system is equal to, let's say, approximately equal to 1 watt per meter squared. And actually it should be power over area, so that we have an intensity. Now, the other description of forcing, according to this article from theconversation.com, he says that changes in solar radiation in a climate model are known as solar forcing. So let's write that mathematically, and we might have something that looks like this. Intensity of the sun in 2022 minus the intensity of the sun in 1750, and this might be where Robert Holmes got his value of 2.29 watts per meter squared. So I'll put a little question mark there and say 2.29 watts per meter squared. So that's a question mark because I don't know where his source was. I don't know where he got that number. But I can say that definitely this value here is not equal to has not been 2.29 watts per meter squared since 1750. Now, I think that 2.89 watts per meter squared might come from the assumption that a significant decline in the sunspot activity during the 17th century was a period of reduced solar radiation. If we had a period of reduced solar radiation, then it might have been as much as 2.29 watts per meter squared less. Now, when I read this, I'll tell you what my interpretation is of it. First of all, I want to say I do not agree on a factual basis that this is true. And this is something, I don't know if some people have difficulty getting around. That sometimes you can take some numbers that aren't actually correct and then actually draw conclusions from those numbers and find out what the result would be. So and the result comes out. The result is false, but it's only the only reason the only reason that the result is false is because the initial numbers that you plugged in were flawed. So when these numbers were given, anthropogenic forcing since 1750 has been 2.29 watts per meter squared. I read that literally, And my understanding of it meant that from 2022 to 17, I'm sorry, from 1750 to 2022, a period of 272 years. And I just decided, well, let's roll with that. Let's see what kind of heat we would have pumped into the system. Let's see what that heat could have done. And here again, I'm not saying this is what actually happened. I'm just saying that if we applied the amount of heat that was involved. Well, first of all, let's just figure out what heat. We're going to figure out how many joules per meter squared this is, and we're going to figure out how many joules per meter squared this is if we had that intensity of 2.29 watts per meter squared coming into the system but not leaving. This is what forcing ought to mean. The power in, or the intensity in minus intensity out, is one. If we said that was 2.29 watts per meter squared, we're going to start with 2.29 joules per second per meter squared, multiply by 3,600 seconds in an hour, times 24 hours in a day, times 365 and a quarter days in a year, and times 272 years. And what we get is 19.6 or 19.7 billion joules. 19.7 billion joules per meter squared. Now, how does that reflect on temperature of things? The trouble with actually calculating how much that will affect the temperature is because this 19.7 billion joules per meter squared is going to distribute itself through the air, through the water, through the rock. This is in this part I'm having the air over like the ocean, over the rock, because that's actually usually the way the Earth looks, with a layer of ocean in between the air and the rock. And so what I'm going to do is just assume that this amount of heating just applies to the water, but instead of, I'm going to do something kind of funky. I'm going to assume the water, this is a counterfactual. I'm assuming that the water goes from 0 degrees Celsius to 100 degrees Celsius. And I'm just wanting to know what is the depth of the water that would be raised to 100 degrees Celsius, from just above freezing to just below boiling, by this amount of heat input. Now, you could make this a different kind of problem. You could say, what is the amount of water that would be brought from 15 degrees Celsius and all the way to a boil, which means you'd need to plug in the latent heat of fusion, or latent heat vaporization, and stuff like that. But right now, I'm just going to use MC delta T equals heat, and this is the heat. This is this is the heat per square meter. So I'm actually going to divide this by area and this by area. And I'm going to say that the mass is the density times the volume, C delta T over area equals Q over area. And then, of course, the volume over the area is the height. So rho H C delta T equals Q over A. And then what I want to know is the height, so I'm just going to take H equals Q over A times rho C delta T. And Q over A is the value we just calculated, 19.7 times 10 to the 9th joules per meter squared. The density of water is about 1,000 kilograms per cubic meter. The specific heat of water is 4,186 joules per kilogram degree Celsius, and the change in temperature we're going to put in is 100 degrees Celsius. And the value that you get by plugging in those numbers is 47.06 meters. 47.06 meters, and that would be the depth of the ocean that could be brought all the way from 0 degrees Celsius to 100 degrees Celsius if you added 19.7 times 10 to the 9th joules per meter squared. And this would not just be in one location, this would be worldwide, all the way around the oceans, everywhere in the ocean, everywhere on Earth, if you had this kind of, if you had 2.29 watts per meter squared affecting the Earth for 272 years. If that was the amount of intensity of the sun, or no, I'm sorry, if that was intensity in minus intensity out for that whole time. So that is what you would get. However, that was taken from context. I took that from the context here because he says anthropogenic forcings since 1750. If you take that from context, there is no way that he could possibly mean the difference between the intensity of the sun at 2222 versus 1750. You understand that the way the sentence is constructed implies that he cannot mean intensity of the sun in 2022 minus intensity of the sun in 1750, because you just can't, there's no way that this means 2.29 watts per meter squared since 1750. It means a change in the input intensity. It just doesn't fit with this sentence construction that he gives here. But what he does then is he does the math as though what he said is this. Because what he does with the math is he basically figures out, okay, intensity, okay, and this is intensity from the sun, and actually, honestly, it's not even that. It's not even intensity from the sun. It's the way he does the math is not the intensity from the sun. It's the outgoing intensity from the Earth. What he calculates then, this is what he does. He does the calculation. Intensity from Earth in 22 minus intensity from Earth 1750 is equal to 2.29 watts per meter squared. This is what the math that he actually does represents. And in an equation form, it would look like this. Sigma T2 to the fourth minus sigma T1 to the fourth equals 2.29 watts per meter squared. And what he does then is he he pulls this 242 number out of this. And I don't know where he gets this 242, but it does resolve to 255.259. So, you know what? I'm going to go ahead and just replace. I'm just going to replace the sigma T1 to the fourth with 242 here. 242. This is essentially what he does, because that's the number that he uses to calculate T1. And then you add 242 to both sides. I don't think this is too difficult. You're adding 242 to both sides, you're dividing by sigma, and then you're taking the fourth root. And sigma is 5.67 times 10 to the negative 8, so the value that he gets for the temperature is 256.2 Kelvin. Meanwhile, he also sets those two things equal and finds that this temperature is 242 divided by Boltzmann's constant and takes a fourth root and gets 255.6 Kelvin. And the difference between these two temperatures is, I should have kept more significant digits, but it comes out to be about 0.6 Kelvin. So this would be the change in the color temperature of the Earth if we made this assumption. If we made the assumption that the intensity of the light, or basically, first of all, we got to assume that the light is actually producing a Planck spectrum. That's an important qualification there. That if we assume that the light is producing a Planck spectrum, was producing a Planck spectrum in 1750 and was producing a Planck spectrum in 2022. Both of those are approximately true, but they're probably not exactly true. But anyway, if and then we also have this other counterfactual that either of those times, well, actually, I think this might be a fairly good assumption that the actual total intensity coming from Earth is somewhere in this range, 242 watts per meter squared, or 255 watts per meter squared. Those are that's somewhere in the ballpark of where the intensity of the average intensity of the light coming from Earth actually is. I'm sorry, not 242 and 244. Those are in the ballpark of the amount of intensity coming out of the surface of Earth. But remember, these temperatures were derived from the assumption that the intensity from the Earth in 2022 was 244.29 watts per meter squared. 244.29. And the intensity from Earth in 1750 was 242 watts per meter squared. And so this concept of it affecting the color temperature by 0.6 Kelvin would be valid under those assumptions, that the intensity from Earth in 2022 was different from the intensity from the Earth in 1750. That would be a valid calculation based on those assumptions. But I mean, is that what he's described here? According to the IPCC, anthropogenic forcing since 1750 have been 2.29 watts per meter squared. I don't know. I can't tell you 100% that this is the way you must interpret his statement, but when I read it, I interpreted it as meaning the intensity in minus the intensity out has been 2.29 watts per meter squared for the last 272 years. If this is what he meant, by saying that it's been 2.29 watts per meter squared since 1750, then that would mean that there would be an extra 19.7 billion joules of energy in the Earth and atmosphere system, which would be sufficient to raise the temperature of water, or raise, where's my, to raise 47 a column, well, every column of water, or the entire ocean, raised the top 47 meters of ocean from 0 degrees Celsius to 100 degrees Celsius. So this is what forcing means to me. It means a forcing in, like pushing something in and not letting it out. That's essentially what it means. But I would call this concept an intensity change rather than a forcing. But I'm not the judge of all semantics, but that is what I would do personally. I would not call this concept forcing. That is just a change. That is just a change in the intensity.